Hi guys, we are starting from slide number 41 of our introduction to semiconductors, and I think by now you know what is a free electron. A free electron is an electron that would have acquired some energy and escapes from the valence band to the conduction band. And when it is now in the conduction band, we say it is now a free electron. And it is free electrons that are responsible for carrying charge. And it is a fact that metals or conductors have many free electrons. You will see from the following slide that there is no forbidden gap between the valence band and the conduction band, and that on its own means a lot of free electrons. So we are now going to discuss the energy band theory of solids that we are going to use to distinguish conductors from insulators and from semiconductors, and you must know it by heart. Right, that's the energy band diagram for the three types of materials: the conductors, insulators, and semiconductors. And please, let's start with the metal semiconductors. Sorry, metal in brackets, metals are conductors. So you can see that there is an overlap between the conduction band and the valence band. So in other words, some electrons have already moved from the valence band to the conduction band. So that is the reason why a conductor or a metal is said to be a good conductor of electricity. Why? Because it has got many free electrons. But an insulator, let's see the energy gap or the forbidden energy gap between the conduction band and the valence band. You can see that about 5 electron volts is needed for an electron to escape from the valence band to the conduction band. So there is a large forbidden gap between the conduction band and the valence band. That is the reason why insulators are bad conductors of electricity. You know, those O-level definitions, they are now a thing of the past. Right, let's go to semiconductors. Right, when we compare the semiconductors to insulators, you can see that the forbidden gap is very, very narrow. In other words, we need about 1 electron volt for an electron to escape from the valence band to the conduction band. So that basically is an illustration of the differences in terms of energy band between conductors, insulators, and semiconductors. Right, that slide is simply describing the previous slide, and it is describing the insulator. You can see that it is a very wide forbidden energy gap. So we need 5 electron volts or more for an electron to escape from the valence band to the conduction band. The rest you can read for yourself. Then that slide is simply describing the semiconductor, and in this case we are saying we need 1 electron volt for an electron to escape from the valence band to the conduction band, or for it to be a free electron. And for germanium, it is said to be 0.2 electron volts, and for silicon it is said to be 1.12 electron volts. So what that means is when we compare germanium and silicon, we can say that germanium is not stable, which means that if you increase heat, or if you increase the voltage or temperature to a device made from germanium, it will conduct heavily. Whereas silicon, as temperature increases, it remains stable. So the energy provided by heat at room temperature is sufficient to lift electrons from the valence band to the conduction band. Some electrons do jump the gap and go into the conduction band. You can go through the rest, right? Let's look at those. The properties of semiconductors are very, very important, and you must know them. And the first one is describing resistivity of a semiconductor as being less than that of an insulator, but more than that of a conductor. Resistivity, you cover it under your EET course. Instead of referring to resistivity, you can also refer to conductivity of a semiconductor. So a semiconductor is almost filled the valence band. What does that mean? Conductors, normally like copper, it has got one electron in its outermost shell, in the valence shell, but for a semiconductor it has got 4. And as you increase the number of electrons in the outermost shell, what that means is conductivity is reducing. So a semiconductor is got a negative temperature coefficient of resistance. You know what this means. When a suitable metallic impurity such as arsenic is added to a semiconductor, its current conductivity, in other words, they increase. Then a semiconductor is formed by covalent bonds. This you know, and a semiconductor is a crystalline structure. This, guys, you know, right? We are now going deeper and deeper. Let's look at the intrinsic semiconductors. This is simply a pure semiconductor. In other words, no impurities have been added to improve the conductivity. So to make a semiconductor device, the very first step is to obtain a sample of a semiconductor in its purest form. And you can see it is stated that there must be 1 part impurity in every 100 million parts of the semiconductor. So such a measurement gives us the definition of an intrinsic semiconductor. Then when atoms bond together to form molecules of matter, each atom attempts to acquire 8 electrons through what? Covalent bond, because an atom with less than 8 electrons is said to be unstable. Then the atoms align themselves in a uniform 3-dimensional pattern to each atom through covalent bond by means of and each atom is surrounded by 4 atoms. Those 4 atoms, it means each one is donating 1. So we end up having 2, one from the semiconductor and another one from another semiconductor when it comes to intrinsic semiconductors. So they will be sharing 2. So such a pattern, we call it a crystal, right? Like what is shown on that slide. You can see that we've got all are semiconductors. Why? Because we've got 4 electrons, and that shell represented is the outermost shell. So you can see that. Let's have a look at the center valence shell. Each one is surrounded by 4, or is sharing electrons with 4. So it now becomes very stable because it now has got 8 electrons in its valence shell. Then that slide is simply describing the previous slide, and is saying the core represents the nucleus and all the orbiting electrons except the valence electrons, since there are as many protons. Okay, let me explain that slide. What he's saying is, since there are many protons in the nucleus as there are electrons orbiting it, the core will have an excess of +4 charge. Why +4? Because those 4 are in the valence band. So at the center, we are going to have 14 protons and 10 electrons. So that +4 is simply referring to it that we have got 10 electrons at the core. So because we have got more protons than electrons, it means we have got a +4 charge, because we know that protons are positive charge and electrons are negatively charged. So you can go through this slide and finish. There is nothing very right. That slide now is very important. And what is happening there? When an electron breaks a covalent bond and moves away, a vacancy is created. This we know very much, and we call it a hole. So what is happening is an electron has acquired some energy and it has moved. But that hole is going to be occupied by another electron. And the other electron is going to occupy that hole which has been left by an electron that occupied the first hole. So in other words, we are going to have an electron and a hole moving in different directions. Therefore, the concentration of free electrons and holes will always be equal in an intrinsic semiconductor. This point is very important because we haven't added any impurities. So holes and electrons are equal in number. And this type of generation of free electron hole pairs, we call it thermal generation. So you can see that the electron is escaping from the valence band to the conduction band. You can just trace the movement of the electron from the crystal. Right. As soon as an electron hole pair is generated, an electron leaves the covalent bond and occupies the conduction band. In other words, it is now a free electron. Like when you have parted ways with your loved ones, maybe he or she has been snatched by the other guy or a lady. We now say you are now a free electron, and if anyone just passes by, you are gone. So we say that a positive charge is associated with a hole, or a hole is positively charged. Why? Because it has the capability to attract an electron. So we can simply say, if a guy is not attached to any lady, we say he is positively charged. Why? Because he has got the capability of attracting any lady. So just go through the slide. Then both types of charge carriers move randomly or haphazardly in the crystal. The random movement of free electrons is easy to understand. A free charge moves in the crystal because of thermal energy. So in intrinsic semiconductors, it's conduction due to thermal generation of charge carriers, and we say this gives rise to a zigzag or random motion similar to gas molecules moving in a gas container. Guys, you can go through the notes. Right. We are now seeing the movement of an electron, and from, if you follow A, B, C, D, E, you will see that movement of a hole through a semiconductor a crystal is in the opposite direction to the movement of an electron. So that is to say, if an electron is going to the left, the hole will be going to the right. So first, an electron has escaped from A an electron at B is going to occupy the wall that has been left by an electron that has escaped from A, and an electron from C is going to occupy a wall that has been left by an electron that is at position B. So if you follow that diagram, you can see that the direction of the movement of an electron is opposite to that of a wall. So the movement of a wall through a semiconductor material, you can see the zigzag pattern. This you can follow, guys. Then you can see that the movement of the wall from A to C in the crystal can be shown in the energy band diagram as shown in the previous slide. An electron is jumping from the valence band to the conduction band, leaving behind a wall at A. Then we have an electron at B moving to A, and sometime later another electron at C is moving to B. So we have got an electron that is moved from C to A, and in the opposite direction a wall is moved. So this jumping movement of valence electrons need not to be considered at all, since we are concerned about the net effect, which is the movement of walls. Right, recombination means that when an electron leaves, or when it gains energy, it moves from the valence band to the conduction band, leaving a wall. But that electron can also occupy, can also fall back to the wall that it has left when it loses energy, and we call that recombination. And the average time that an electron remains free, we call it its lifetime. I don't know if we human beings have got lifetimes. Let's say a husband has passed on. The lifetime of a lady is the time that she can remain without getting in love again. So at any instance, both types of charge carriers are present in equal numbers at a given temperature. We are looking at an intrinsic semiconductor, and that point is very, very important. We are going, guys. We've got no time to waste. What are we saying? The random movement of electrons and holes gets modified over and above random motion. There also occurs a net movement called a drift. And what are we saying about a drift? There is not much. Although the two types of charge carriers move in opposite directions, the two currents are in the same directions, and that means they add together. And we are talking about an intrinsic semiconductor as shown on that diagram. The I subscript N plus I subscript P, they are adding, and we say total conventional current is equal to IN plus I subscript P. That's where the phrase adding is coming from. Then when the flow of carriers is due to an applied voltage, so we can have the flow of charge carriers due to thermal agitation or due to thermal generation. But when the flow of charge carriers is now due to an applied potential difference, we now call it the drift current. And a second type of current may also exist in a semiconductor. This current is called diffusion current, and it flows as a result of the gradient of carrier concentration. I think you know what diffusion means from your O level. I will emphasize where you must direct your effort to. So that slide is simply explaining that is the semiconductor is a negative temperature coefficient of resistance. This you know. Intrinsic semiconductors are of little use. That is, they can be used as heat or light sensitive resistance. But practically all semiconductor devices are made of semiconductor material to which certain types of impurities have been added. And these impurities that we are referring to are group 3 elements and group 5 elements. And the process of deliberately adding impurities to a semiconductor material, we call it doping. Please, it's a very important term. You must be able to define it. And doping is done after the semiconductor material has been refined to a large degree of purity, 1 impurity in every 100 million. So a doped semiconductor, we call it an extrinsic semiconductor. Right, we are now considering a situation whereby we are adding a pentavalent, then after that we are going to add a trivalent. By pentavalent, we are simply referring to group 5 elements, those with 5 electrons in their valency shell. And you must know some examples of pentavalent atoms, thus phosphorus, arsenic, antimony, blah, blah, blah. So if the amount of impurities is very small, we can safely assume each impurity atom is surrounded or around by silicon atoms. Let's go to the next slide. Right. We are adding a phosphorus atom to a silicon crystal, and the impurity atom phosphorus in this case is at the center. The plus 5 at the center is showing that it has got 5 valence electrons. Right, then we've got a 5th electron that is not attached to any atom, and that 5th electron is originated from the phosphorus atom. So we say phosphorus is a donor atom in that case. Why is it excess? It is because all the other 4 electrons are being shared together with 4 adjacent silicon atoms. So that material, we call it an N-type semiconductor. Where is the N coming from? It is simply coming from the charge of an electron, which is negative. So it's a negative type semiconductor. If you are asked to describe the formation of or the process of doping using a pentavalent atom, please, you must take note of the fact that the phosphorus atom or the pentavalent atom must be at the center, surrounded by silicon or germanium atoms. So that diagram is simply explaining what I have been saying. We have got the donor, we have got that it donates an electron, and what are we saying? Let me stress this point, that because thus the number of free electrons becomes far greater than the number of holes if we keep on adding some impurities. So we say that is why we can say that an N-type semiconductor has electrons as majority charge carriers, but we also, due to thermal agitation, have some minority charge carriers. And in an N-type semiconductor, minority charge carriers are holes. Guys, take note of that. Then in the designation, the N-type semiconductor, the letter N stands for negative charges. We have discussed that one. The negative charge of the electron is thus generated is exactly balanced by the positive charge of holes. Alright, in an N-type semiconductor, there are additional free electrons created because of the addition of the donor atoms. Then the negative charge of these electrons is again balanced by the positive charge of the immobile ions. We've got some ions that don't move, and you know the definition of ion is an atom that has lost or gained an electrons. So the total number of holes and immobile ions is exactly the same as the total number of free carriers created. I think there were some individuals who were referring or who were asking about such a process. How does that happen? I think you can get it from that slide or from that explanation, right? That's an illustration of the construction of any type semiconductor. So we've got some negative mobile charge ions. These don't move. Those dots are representing the electrons, but we also have some thermally generated holes, which are minority charge carriers in any type semiconductor. Right, we are now going to P-type semiconductor. P simply stands for positive. And what are we saying? We are now adding some group 3 elements as impurities, or group 3 atom SN impurities. And some examples include indium, boron, etc. You can refer to the table in the previous video lecture presentation. So we are going to use the boron atom, and we are adding it to a silicon crystal or germanium crystal. And one very important thing which we must know is a boron has got 3 electrons in the valence shell. Let's see what happens if we add it to a crystal of germanium or silicon. Right, that diagram is simply showing us the effect. Because it has got 3, it will donate 1 electron to a silicon or germanium atom on its left, then to another atom on its right, and to another atom below it. Then to the atom above it, it has got nothing to donate, so they cannot share. So we say that gap is capable of being filled by an electron. So it has the capability of attracting an electron. So if there's that capability, then it means it has got a positive charge. Hence the name P-type semiconductor. I hope it makes sense, and you can illustrate and describe that. That slide is simply explaining, and what I can only add is a donor. The group 3 element that we have added is called an acceptor, because it is capable of accepting or attracting an electron. And because it is a hole, we say in P-type semiconductor, majority charge carriers are holes, but due to thermal agitation, we have got also some electrons as minority charge carriers. In the general illustration of a P-type semiconductor, you can consult any book you feel like. It's because some other books don't put the immobile ions. It will be correct as well. So you can see that what are many there, holes, those circles are many than the black dots. So we say majority charge carriers are holes and minority charge carriers are electrons. So this is the end of introduction to semiconductors.